Hello, everyone. Today, I'm going to introduce a general model for control chart and short control chart for individual measurement and short control chart for attribute data. Let's consider a general sample statistic W, which can be sample mean, sample standard deviation, sample variance, or sample range. For a sample statistic, a general control chart model can be mu W plus minus L sigma W for upper control limit and lower control limit, and mu W for central line. Here, mu W and sigma W are the in control mean and standard deviation, respectively. This means that if we know mu W and sigma W of the sample statistic, then we can simply apply them into the formula and establish its control chart. For example, let's consider X bar chart. For X bar chart, we know the exact distribution of mu X follows, which is a normal mu 0 and sigma 0 square divided by n. So we can apply them into the general model, then we can establish the same X bar chart we learned in the previous lecture. For R chart, similarly, we need mu R and sigma R, but unfortunately, they are not in a simple distribution form as X bar chart does. The good news is that statisticians have already figured out good approximations. So mu R and sigma R can be approximated by D2 sigma 0 and D3 sigma 0 respectively. D2 and D3 are constants whose values depend on n. This table shows D2 and D3 values for various sample size. As explained, they can be used to approximate mu R and sigma R. For example, if the sample size is 5, then corresponding D2 and D3 values are 2.326 and 0.864. So we just plug in those values to the formula, then we can easily approximate mu R and sigma R. Besides D2 and D3, the table provides approximation constants for other sample statistics. S chart also can be established by the general model. The sample standard deviation formula is known, but its probabilistic distribution is complicated, so we can approximate using C4 value, whose values also depend on sample size, and we can find their values from the same table. Similarly, by applying the general model, we can easily establish S chart. So far, we have discussed control chart whose sample size is greater than 1 and established control chart based on sample statistics. What if sample size equals to 1? For the case, the short control chart for individual measurement was developed. Individual measurement are very common in many transactional business and service processes. Sometimes this happens because there are large time gaps between service activities. The key idea is to use the moving range of two successive observations as the basis of estimating the process and the variability. Let's define MR by the difference between successive observations. Then we can get subgroups that consist of MRs, each of which has 2 observations. Let me introduce 2 types of a short control chart for individual measurement. One is the control chart on individual unit, and the other one is the one on MRs. If you are interested in monitoring X observations, then you can use the first one. And if you are interested in monitoring MRs, then you can use the second one, moving range control chart. Now let's talk about short control chart for attribute data. Detection based on discrete data or attribute data are very important in practice. And it is especially so in the application of healthcare or security surveillance. For example, count of modality, ER visit, and accident. However, the control chart, what we have learned is not applicable to attribute data, mainly because attribute data do not follow normal distribution. Discrete data typically follow three types of distribution: hypergeometric distribution, binomial distribution, and Poisson distribution. They have their own usages. Accordingly, their probability mass functions, PMF, are different, as shown in the slide. The main difference is the number of parameters in the PMF. Hypergeometric PMF involves 3 parameters, N and capital N, D. Binomial PMF involves 2 parameters, N and P. Lastly, Poisson PMF involves 1 parameter, lambda. One can use the distribution to approximate another one. In general, hypergeometric distribution provides more accurate but less flexible data distribution, while a Poisson distribution gives more flexible but less accurate data distribution. As a control chart for continuous data assumes normal distribution, control chart for discrete data assumes one of these distribution. Control chart for attribute data are often called attribute control chart. 2 rudimentary attribute chart are P chart and U chart. P chart is for detecting the non-conforming rate or defective rate in a sample. The non-conforming rate of each sample can be calculated as P, which is D divided by N, where D is the number of the defective items in a sample and N is a sample size. A plot of P versus the sample index is called the P chart. The cardboard cans data in an example of is an example of discrete data. From the number of conforming cans in a sample whose size is 50. So we can calculate the defective rate in a sample. So in this case, we can say that the number of defective items in a sample follows a binomial distribution where n equal to 50 and d is the defective rate. So let's consider sample statistic P. Since we know mu P and sigma P, we just apply a general model to construct control chart. If P is unknown, we need to estimate it from historical training data. Suppose that there are m historical samples, then we take average of defective rate to estimate it. This figure shows the P chart of the cardboard cans example for the case where L equal to 3 in the formula. We see there are 2 out of control samples at 15th and 23rd samples. The other attribute control chart is a U chart, which is interested in detecting a change in the average number of defects per inspection unit. The number of defects per inspection unit, U is assumed to follow Poisson distribution. If U follows Poisson distribution and there are n inspection unit in a sample, sample mean is lambda and the sample variance gonna be lambda divided by n. Then we apply general control chart model and obtain U chart. The parameter lambda in a Poisson distribution is assumed to be given, or we can estimate it from historical samples. Here is an exercise problem. The manufacturer wishes to set up a control chart at the final inspection station for a vending machine. Defect in workmanship and visual quality features are checked in this inspection. For the past 22 working days, 198 machines were inspected and a total of 1,089 nonconformity reported. Using two machines as the inspection unit, calculate the center line and control limit that are consist with the past 22 days of inspection data. Now, first of all, we estimate lambda, which is the average number of nonconformity per inspection unit. 1,089 divided by 198 is the average number of nonconformity per machine, right? And because inspection unit consists of two machines, lambda hat should be 1,089 divided by 198 times 2, which is 11. In this example, no mention about sample size, so we regard one inspection unit as a sample, which means n equal to 1. Then we can compute upper control limit, lower control limit, and central line as shown in the slide. Okay, there are two variants of P chart and U chart, which are MP chart and C chart. The total number of a defective item is of interest in MP chart, and the total number of defects in a sample of size n is of interest in C chart. For example, the cardboard cans example, the chart was NP chart, right? So actually, NP chart or C chart is nothing but P chart or U chart with everything multiplied by a factor of n. So we skip the details of the NP chart and C chart in this course. Okay, thank you.